This lecture will introduce you to the strategy I call the proof bits strategy. The way the proof bits strategy works is it works like little modules that you can stick into a proof. They're just sort of little plug and play modules. These are the proof bits are little short proofs that are sort of patterns of inference that come up over and over again. So if you memorize these short little proofs, then when you come up against a situation where having one of these things would be useful, then you can go ahead and do it very easily. So I'll show you a few proof bits in this lecture, and then I'll show you a proof where they could be used, where one of them could be used. And in your homework, you will see that there are a number of the short little proofs that you have to do, little 3-point proofs, turn out to be proof bits. So you'll want to pay attention to those when you're doing some more complicated proofs. They might come in handy. Okay, so here's one proof bit that could be kind of cute and useful. So suppose you have the formula A. And what you want to get to is the formula not A, arrow A. Now, you could get to this through a complicated sort of a reductio variant on arrow in strategy. You could do that. But now that we have the rules of replacement, you can actually do this much easier. So I'm going to work this proof bit backwards. So I'm going to apply the definition of the conditional backwards to this conditional here. And so I'll have not A or A. So I'm kind of doing a little bit of what we'll talk about in the next lecture, the lecture on the abracadabra strategy, where I'm saying, well, this conclusion is maybe a little difficult to get, so I'm going to turn it into something that's easier. So that'll be by the definition of the conditional. And then once we see that if we had not A or A, then we could get what we want. Then it's very easy to see how we're going to get not A or A. We're going to get that from A by or introduction. On line 1. And so there's a cute little proof that can turn a single letter into a conditional. And really, we see by looking at this actually that what we poofed in could be anything. So actually we could have gotten what we wanted. We actually didn't need this whole convoluted thing because we could have just gone not A, arrow A by the second version of arrow in. But that aside, if you didn't see that right away, you could do it this way too. So, and it would only be one line longer. Let's look at another little proof bit. So suppose we have the formula, it's false that P if and only if Q. And let's suppose we want to get to the formula P and not Q, or Q and not P, for some reason. Well, remember when I talked about the rule of biconditional expansion, this is a perfect case where it's useful to use that. So we can use that rule of biconditional expansion to turn the P if and only if Q into P arrow Q and Q arrow P. And all of that is negated. So that's by 1, this is line 1, BE. And then we can push that negation in using De Morgan's. So we get, it's false that P and, P arrow Q, or it's false that Q arrow P by De Morgan's. And then we can easily see that we can get to this by the definition of the conditional. So in a few short steps, we changed the formula a lot. And that's what we have here on line 4 is a whole lot more useful than what we had on line 1. There's not much we can do with that. Okay, let me see. Let me think of another good one that's good to do. Well, suppose we have the formula not C and A. We'd like to do something useful with that, but we really can't do anything useful with this. So we can transform it using De Morgan's. I guess this is really more of an abracadabra move. But abracadabra moves and proof bits, the difference is that proof bits usually have more steps. And abracadabra is just, an application of a derived rule, of a rule of replacement. That's all an abracadabra move is. So that's all we did here. We did De Morgan's on that. And now it's a whole lot more useful. So you'll have to discover the proof bits for yourself. I'm going to give you a bunch of them as little proofs, and then you're going to have to see how and when they're useful for yourself. It's kind of hard to show you, but you'll see it when it comes up.